if you have a linear function, the slope is always constant. Okay, over here, I still have a function, let's call this f again, we'll call that f again. I still have a function f, and it is decreasing. What about f prime everywhere here? F prime represents the slope of each tangent line as you move along the curve. What's the slope doing as you move along the curve? Let's talk about this kind of a slope. This is a negative slope, but it's not too steep at all. This is still negative, but it's getting a little more and more steep, isn't it? Still negative, more steep, still negative, more steep, still negative, more steep, and so on and so on. When negative numbers get steeper and steeper and steeper, or get bigger, like -2, -3, -4, -5, what's the value actually doing? And it should say that f prime is decreasing as well. The slopes are actually decreasing. Think of up here, maybe the slope might be a 0, but it's not quite a 0. We're going to leave it so that we don't see that relative max right there. We're just barely off the 0 part, and we're getting smaller and smaller and smaller and smaller and smaller. So the slopes are definitely decreasing. Well, this is because, let me see here. The function is decreasing, f prime is decreasing, and this is because f itself is concave down. Okay, this is concave down. And you can see this one over here before we even start is concave up. All right, the function itself is going down, so f is decreasing once again. Let's talk about f prime. Anytime we're talking about f prime, we're talking about the slope of the tangent line, anywhere you come around here. This is a pretty steep negative slope. And then not so steep and not so steep, and we're actually approaching what? We're not hitting it, but we're approaching a flat point, aren't we? So you're going from something that's pretty steep to maybe a -1, to maybe a -1/2, to maybe a -1/3, and we're getting closer and closer to 0. So when you move from the negative, steep numbers on the negative side, get closer and closer to 0, you're actually increasing. So f prime is increasing. Which means the slope of the tangent lines are actually getting bigger. The slope of this tangent line is increasing. Every single tangent line has a negative slope, but they're getting bigger. Okay, and this is because f is concave up. We'll talk about concavity when we get into 3.4, but we already know about concavity. We already had those little whoop whoop things going on back with our polynomial function, so it's not a new term for us, and we're used to the terminology. We're used to the notation that I use. So that, in a nutshell, indicates increasing and decreasing functions. We have yet to get into our first derivative test. Okay? I'm going to erase the board here, and we are going to get down to a first derivative test. A lot of people love the first derivative test. And I like the first derivative test, but I love the second derivative test. That is going to be my favorite. Okay. All right. Yeah, I've got one more thing I have to give you before we hit that test. This is theorem 3.5. And theorem 3.5 is in 3 different parts. One for a positive slope, one for a negative slope, and one for a 0 slope. So we'll talk about that real quick, and then we'll get into our first derivative test. All right, well, let's start right off saying let f be a function that is continuous on the closed interval AB, and I think you already know, differentiable on the open interval from A to B. That's the premise of a lot of theorems, so that doesn't surprise you. Okay, part 1 here to this thing says if f prime of x is greater than 0 for all x values in the interval, And I suppose I could have said an AB, but I'm good. Then, f is increasing on the closed interval AB. Okay, so if f prime of x, now we're talking about a function increasing based on its derivative, not based on its x values compared to its y values of the original function. Now we want to look at its derivative and see whether or not the derivative will tell us something about whether the function is increasing or decreasing, and it certainly does. The derivative represents slope. If the slope is greater than 0, you know what greater than 0 means? Greater than 0 means what? Positive. If the slope is positive, well then, the function f is going to be increasing. And again, it can be increasing constantly. Oh, well, there's a constant slope right here, okay? So the function f is increasing at a constant rate. We could be increasing where we take off kind of slow. We're not increasing very much here at the beginning, but then boom, we start increasing quite a bit along here. So we're still increasing, and look at all my tangent lines have positive slopes. This is concave up. And again, for concave down, we can go ahead and talk about a function increasing even though it's concave down. And function, tangent lines are positive. So if the tangent line is positive, yeah, the function has to be increasing on the interval. I'm going to go one step beyond that, and I'm just going to mention this little example right here, which is one example I like to give you. I'm going to go for the point 2, 1. I'll go for 2, 1. I'm going to draw a little teeny tiny horizontal tangent line, instantaneous rate of change of 0. And from there, I'm going to go concave up and concave down. I'm going to merge these two together. And I want you to see what's happening as I trace my function with my tangent line. I have a positive, very steep slope. It's still positive, but the slope is decreasing. Do you see? When I get right here, my instantaneous rate of change at the point 2, 1 should be 0. That means the slope of the tangent line right there at 2, 1 equals 0. But then what happens? I start increasing again. I definitely start to increase. There's no doubt about it. For any two numbers along here, it works. So I'm increasing on this entire interval, even though this tangent line right here, the slope of this tangent line happens to be 0. And that's a little bit of a thing that we have, and I'm just going to write a note here. And I'm going to word it the way I did. This theorem is still valid if f prime of x equals 0, but only for some finite number of values on the interval. All right. I don't care which 2 points you pick along this interval. Let me advance my chalk a little. I don't care what 2 points you pick along this interval. Doesn't matter. Any two. I don't care. If you compare the x's, you take the x on the left compared to the x on the right. Well, the y on the left would be lower than the y on the right, all the way through. This function is definitely increasing everywhere on its whole entire domain of all real numbers. And, whoops, there we go. Just make sure that you understand that the derivative can equal 0, but only instantaneously, only for a finite number of values on that interval. If I were to draw this function and have a long constant area like that, even though concave down, concave up, if it maintained a constant function for a little bit, this wouldn't work. I can only instantaneously maintain a slope of 0 on it and off it, and I'm done. For a finite, meaning I can count them. Okay? No interval, just one little point. It can do it again at another little point, and another little point, and another little point, but as long as it keeps getting those whoop whoop things and going up in the air, the function will definitely be increasing on the whole entire domain. Okay, let's go back to decreasing, which is going to be 2, if f prime of x is less than 0 for all x in the interval, then f is decreasing on the closed interval between a and b. And I can draw you some pictures. We can go for a decreasing function like this. Isn't that a decreasing function? And isn't the slope of the tangent line, no matter where I am here, isn't this first derivative equal to 0 because the slope of the tangent line, I said equal 0, I should say negative, I apologize. Slope of this line right here, negative. Slope of this line, negative. Slope of this line, negative. Matter of fact, it's consistently the same exact negative as well, because I have a linear function right here. If I talk about concave up and still decreasing, looks like this. This is concave up, but the function is still going down, so therefore the function is decreasing. All of my tangent lines have a slope that is what? Negative. And in mathematics we say negative by writing less than 0. So we have all of our tangent lines having negative slopes. All right? Was negative a lot here, not so much here, even less here, still negative, but my slopes are definitely increasing. Okay? And now I need an example for concave down, but decreasing looks something like this. This is concave down, and yet I'm decreasing. So as I follow my tangent line with the concave down function, I'm negative, but not too much. Still negative, still negative. I'm getting more and more negative the more I go along this curve. Okay, so my negative slopes are definitely getting further and further negative, decreasing. My slopes are decreasing, but my slopes are all negative. And all my slopes being negative means that all my slopes are less than 0. So I can definitely tell whether or not a function is increasing or decreasing on an interval based on its first derivative. This note here carries for this function as well, because I can draw my little horizontal tangent line, and I can fall down, and I can make that concave up, that part, concave down this part. I am instantaneously looking at a slope of 0 for my tangent line, but instantaneously is finite. It means just once. So I can have that. And this whole entire interval is definitely decreasing, even though here it's concave up and here it's concave down. Okay? Let's make sure we understand this concavity just for one more minute. I'm going to erase all of these pictures that I have here. I don't want you to get concave up and concave down confused with increasing and decreasing. One does not mean the other. This function right here I just drew, looks like a quadratic, is completely concave up on its entire domain. And yet, on part of it, we're going down. On the other part of it, we're going up. So we are decreasing, and then we are increasing. This point right here, where I have a slope of the tangent line is definitely going to be a 0, we call that a relative min. So when we switch from a decreasing function to an increasing function, we can only do that at a relative min. Okay, and upside down, so we're talking concave down. I have positive slopes here, positive, 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 all of a sudden, slope is 0, negative, 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 negative. So I have positive slopes here, negative slopes here, and my slope is actually equal to 0 right there. Let me write that over here as well. What kind of slope do I have here? Negative. What kind of slope do I have here? Positive, and of course I have a 0 tangent line right there. Okay. So, third thing, I bet I don't even need to write it. It's the only thing that's not here yet. If f prime of x is equal to 0 for all x in the interval, then f is what? It's not increasing, it's not decreasing, it must be constant on the entire interval between a and b. That wraps up theorem 3.5. And now we can put those concepts together and we can hit a first derivative test. Okay? let's erase this.